Welcome and thank you for watching this video. I'm Wessel and I will present our construction of a canonical form for positive definite matrices. And this joint work with Mathieu Dutour Sikirić, Haensch and John Voight. So one of the main objects we will be considering in this talk are lattices. And given some base factors, a lattice consists of all intercombinations of these base factors. And such a base is not unique. In dimension 2 or above, every lattice has an infinite number of different bases. So a good question would be, given two bases, do they generate the same lattice? And it's easy to see that this is only the case if there is some unimolar transformation, so a matrix that's integer and is determinant 1, such that B1 times U is equal to B2. And to obtain this transformation, you can just use simple linear algebra and check if this transformation is actually unimolar. But what if you have many bases? So B1 until Bm, for m maybe a million or a billion. Then we have to do m squared pairwise checks in the worst case. This might be unfeasible. So to solve this, we look at the Hermite normal form. And this only works for B integer. And then the Hermite normal form is the unique basis of the lattice generated by B, such that H is in column echelon form, and left of the pivot elements are non-negative and strictly smaller than the pivot. This is different from a reduced echelon form because now we can only do insert transformations. An example of this is the following basis. And now we have a polytime algorithm to compute the Hermite normal form, and this uses LL to prevent the coefficient blowup. Now, the nice thing about this Hermite normal form is that two bases generate the same lattice, if and only if their Hermite normal form is the same. And this Hermite normal form is what we call a canonical function. Another way to state this is that to say that the output of the Hermite normal form is independent of any unimolar transformation on the input. So to solve our problem, we just compute the Hermite normal form of all these M forms, which is at least linear in M. And then we only have to check for equality. And this can easily be done by using a hash table or maybe sorting in at most OM or OM log M steps, which is a great improvement on the M squared. Of course, this is the Hermite normal form is for unimolar transformation on the right, but we can, by taking transpositions, we can also define a similar function that's canonical for transformation on the left. So the second object we will be considering are graphs. So in our case, graphs are numbered 1 to n, and the edges are just pairs of these vertices. And we call two graphs equal if these edge sets are equal. And this also allows to define graph automorphisms. And the stabilizer of a graph, so a graph automorphism, is a permutation that permutes the vertex numbers such that the eventual edge set is still the same. So in this example, we could swap vertex 1 and 3 without changing the edge set. However, if these numbers are somewhat scrambled, but these graphs have the same structure, we still want to call these graphs isomorphic. And we define this as follows: two graphs are isomorphic. Oh, I see, I noticed the edge here. If and only if there is some permutation such that of the vertices such that they become equal. So to come back to this idea of a canonical function, we would like to give a vertex ordering of the graph purely based on the graph structure, such that if two graphs are isomorphic, then these canonical forms or this canonical ordering should be the same. In some sense, we would want to ignore the original numbering of the input vertices. An example of this is a vertex order that minimizes the edge set under some lexicographic ordering. And note that the permutation that goes from the original graph to this canonical form is only unique up to the stabilizer, because elements in the stabilizer don't change the edge set. Now, what's more generally, for weighted complete graphs with weights on the edges and on the vertices, we can say that two graphs are isomorphic if and only after some permutations all these weights are the same. And actually we can do this. So there exists several canonical graph ordering implementations in libraries such as Naughty, Bliss, and Traces. And the practical complexity is rather good. So most graphs up to thousands of vertices are no problem whatsoever. The theoretical complexity is a bit more difficult. And only in 2015, Babai pushed a paper on arXiv that showed that graph isomorphism can be solved in quasi-polynomial time. And this was accepted in 2016. However, in 2017, this was retracted after Helfgott found a flaw in the proof. And luckily, this was almost immediately fixed, and this was confirmed by Helfgott in an extended exposé. However, this was just for the graph isomorphism problem, so finding this permutation. And we want to have a canonical ordering in quasi-polynomial time. And luckily, Babai gave that to us in a paper he published in 2019. So now I come back to the main problem we are interested in, namely lattice isomorphism. So suppose we have a lattice with a basis, and we rotate this base a little bit, or more generally, we have some orthonormal transformation. And then we look at the lattice that this base generates. Now, these two lattices have in some sense the same structure, and that's why we want to call them isomorphic or isometric. Note that if we have these two bases, then it's easy to see what orthonormal transformation we've used. It's simple linear algebra. However, if one of these lattices is given by a different basis that are is incompatible with the other, then this becomes a lot more difficult to find. So by definition, two lattices are isomorphic if there is some orthonormal transformation that maps one onto the other. In terms of the basis matrices, this means that there is some orthonormal transformation on the left and some unimolar transformation on the right, such that B1 is mapped to B2. And note that if either the orthonormal transformation or the unimolar transformation is trivial, then it's just simple linear algebra to find the other one. However, in the general case, it's not true. So to simplify things a bit, we can look at the gram matrix. This removes the orthonormal transformation at the cost of an extra U transpose. And this brings us to quadratic forms. So a gram matrix A, which is equal to B transpose B, induces a quadratic form given by X maps to X transpose AX. And the nice thing about such a quadratic form is that it remains all geometric information about the lattice. We can still take all inner products. Now we call A1 arithmetically equivalent to A2 if there is some unimolar transformation U, such that U transpose A1 U is equal to A2. And this is the same basically as the lattice isomorphism. And note that this U is unique up to the stabilizer of A1, which we define as all unimolar transformations that keep A1 fixed. Now our main goal is to construct a canonical function, and this should satisfy two properties. First, the output of a canonical function should be arithmetical equivalent to the input. And secondly, if two forms are arithmetical equivalent, then their canonical form should be the same. And we can slightly rephrase the second property using the first property by saying that the canonical form should be independent of any unimolar transformation on the input. So I mentioned before that it becomes difficult when these two bases don't map onto each other by this orthonormal transformation. So maybe it's nice to look at sets of lattice points that are actually mapped onto each other by the orthonormal transformation. And one of these sets is, for example, all points up to some norm. Because this transformation is orthonormal, these sets have to be mapped onto each other. Now back to the quadratic forms. This gives us a characteristic vector set, which for each quadratic form we have some set of integer vectors of the same dimension as the form, and this should satisfy two properties. First, the set should generate the whole of C to the D as a C module. This is equivalent to, in the lattice terminology, as saying that these points should generate the whole lattice. And secondly, we have this transformation property, which basically says that this set is independent of the basis. Now, the second property is satisfied by, for example, this set of bounded elements with respect to the quadratic form. And for the first property, we can just say, okay, we take the bound minimal such that this first property is satisfied. And this allows us to define a characteristic vector set. Now, what's nice about this set is that it can be used as a proxy. So if A1 is equal to U transpose A2U, then this is equivalent to saying that U maps the characteristic vector set of A1 onto the characteristic vector set of A2. And this was already used by Plessin and Sauvigny to compute lattice automorphisms and isomorphisms. So what we actually did is we turned this action U transpose U on both sides to a single action on the left of U. And now if you remember the Hermite normal form, this seems like something we can use here. However, the Hermite normal form acts on a matrix, and this equality is only as a set. So to use the Hermite normal form, we would have to turn these vector sets into a matrix. But by doing this, we choose some ordering that's not necessarily canonical. And this is the problematic. So we zoom in a bit more. So suppose A1 is equal to U transpose A2U, like before. And we have this vector set of A1. And we have the vector set of A2, which is just U times the one of A1. And suppose it's nicely ordered like this. So it's exactly equal to, the first element is U V1 and the last element is U Vn. Now under this ordering, we necessarily have that all equal pairwise inner products are the same. All pairwise inner products are the same. So the inner products of the Vi, Vj with respect to A1 are equal to those of Wi, Wj with respect to A2. And actually, having this equality for all these I and j is also sufficient for such a U to exist in the first place. But in general, these vector sets don't have this overlapping ordering. That's perfect. So we just have this second vector set. And what we've shown here is that the goal actually becomes to find a permutation such that after this permutation, these pairwise inner products are the same. Because if we have done that, then we can also compute this U by simple linear algebra, and we're done. Note that this all this thing about equal pairwise inner products sounds a lot like graph isomorphisms. And indeed, we can define a graph where the vertices are represented by the elements of the vector sets, and the weights are exactly all these pairwise inner products. And now the definition that there must exist such a permutation such that the pairwise inner products are the same is exactly the definition of that these graphs are isomorphic. And so this all becomes a graph isomorphism problem. Note on top of that the stabilizer of the form is isomorphic to the stabilizer of these graphs. You can make this explicit. So this would solve the lattice isometry problem, but we are interested in finding a canonical form. And it makes sense to use a canonical graph algorithm for this. So we use a canonical graph algorithm to get some canonical ordering of these graphs. And suppose this looks like the following. Now we know that this canonical ordering of the graph is unique up to the stabilizer of the graph, which is isomorphic to the stabilizer of the original form. And actually this, if you translate this back, then this means that this ordering is unique up to some element of the stabilizer. So actually this defines a matrix up to the stabilizer of A that has the following canonical property, namely this transformation property that the characteristic vector set had. However, in this case, it is a property of on a matrix and not under set equivalence. And because these stabilizer elements are also unimodular, this allows us just to use the Hermite normal form to get rid of all these unimodular or stabilizer transformations on the left. So this Hermite normal form of this constructed matrix actually gives some kind of canonical label to a form. However, we now want to translate this back to actually obtain a canonical form. So let TA be the unique transformation such that the matrix MA is equal to TA times the Hermite normal form of MA. Note that because MA is uniquely defined up to the stabilizer of A, this TA will also be uniquely defined up to the stabilizer of A. However, we can still define our canonical function of A as TA transpose A times TA. And note that this stabilizer, that's up to the stabilizer, doesn't matter for this because it all cancels to the A. So what remains to show is that this is actually a canonical function. Well, for this we also used that if you would apply this transformation, find this transformation of U transpose AU, then this is equal to U inverse times the transformation of A. And this up to the stabilizer of U transpose AU. This is exactly because if you look at the matrix corresponding to U transpose AU, this is exactly the same as U inverse times MA up to the stabilizer. And now it's just a simple matter of filling it in. So if you look at the canonical form of U transpose AU and you work out the details, you see that it's exactly the same as canonical form of A. And of course, the output of this canonical form is equivalent to the input because we've only applied a unimodular transformation in the definition. So we've succeeded in building our canonical form. A quick note about the theoretical complexity. So suppose A is defined over a computable subfield F of the real numbers. Then we define another characteristic set function based on the Voight relevant factors. And this has the nice properties that it sizes at most single exponential in the dimension, and it can also be computed in a single exponential number of arithmetical operations over F. And now the eventual graph will also be of single exponential size, and we apply a quasi-polynomial canonical graph algorithm to this. And if you combine all of this, we get a complexity that's exponential in the dimension in terms of arithmetical operations over F. And for F as Q, we can show that these operations are polynomial bounded in the input size of A. And a short note on the practical complexity. Well, it's efficient in practice. We have implementation, and it's in the order of milliseconds or a few seconds up to dimension 20, even for like laminated lattices, word lattices, random lattices, perfect lattices, etc. Above this, we can still compute it, for example, for random lattices, but we need to use exact arithmetic, which slows down things a lot. Now, some applications. Well, in general, the main application is removing redundant forms in a large collection. And this is often a critical bottleneck in enumeration algorithms, such as Canonical method and Voigt's algorithm. So what these methods do is they generate a lot of forms, and then they have to remove the duplicates to find just a complete list of what they want to find. So more specific examples are enumeration of forms of bounded discriminant or small spinor class number. Some examples of tables are this. Secondly, perfect form enumeration to solve the lattice packing problem. And estimates are that they're in order of 1 billion perfect forms in dimension 9. And if you run this enumeration, you are expected to find maybe like 50 billion or 100 billion of these perfect forms, and you need to remove duplicates. And the nice thing is that the computed canonical form for a perfect form in dimension 9 takes an average of 6 milliseconds, which is similar to just a single arithmetical equivalence check. And it can also be used to compute some algebraic modular forms related to Canonical method. So to conclude, we show an explicit and deterministic algorithm for finding a canonical form for a positive definite matrix under unimodular integral transformations. It's based on canonical graph algorithms and characteristic vector sets, and it's efficient in practice and has many applications. Thank you.